Well, good morning. What I'd like to do this morning is speak to you about the energy storage landscape in a way of introduction. And then I want to talk about innovation, the innovative process, and specifically to show how the invention of the liquid metal battery didn't come from the battery industry at all. It came from electrometallurgy, and how to take these seemingly disparate ideas and put them together for invention. So let's begin with the energy storage landscape. As a professor, I have to begin with a history lesson. The battery was invented not far from here in Padua by Professor Alessandro Volta. And this happened about 200 years ago. This is his first battery, a stack of coins, different metals separated by cardboard soaked in brine. And this gave birth to a new field of science, electrochemistry, but immediately gave birth to a new field of technology, electroplating, electroforming, and formed the basis for electrolytic production of metals ultimately. Perhaps overlooked is the fact that with this invention of the battery, Professor Volta for the first time proved the utility of a professor. Until Volta, nobody believed a professor could be of any use, but he showed that professors have some utility. Now, people think that not much has changed with batteries, but that's not true. If you take a look at the rechargeable batteries, you see lead-acid batteries at 35 watt-hours per kilogram, and then over the years now we have lithium-ion at 150. So there has been some progress. But just to be a little bit sobering, gasoline in these same units is 12,000. And this is why the electric vehicle is so elusive, because the energy density of liquid fuel is so high. This is why we use liquid fuel. So you say, why would somebody change from 12,000 to 150? Well, we have an environmental imperative. And the environmental imperative makes us work very hard to effect this change. Now, there's no best battery, just as if I came to you and I said, what is the best wine? You would say, what do you mean, what is the best wine? What is the meal? What is the occasion? And so on. So don't pay for attributes you don't need. So for example, the cell phone needs to be idiot-proof. Some people think it's mainly in the hands of idiots, so you have to be very careful with it. The car needs to be crash-worthy. So we cannot simply take the batteries that we've developed for cell phones and scale them up because they will catch fire. We have to be prepared for this. The airplane needs to be fire resistant. We know about the recent mishaps with the 787, the first airplane to put the lithium-ion battery, and they blundered in their design. What about service temperature? Well, it comes down to human contact. If the battery is going to your face, it must be at room temperature. But for stationary storage, it doesn't matter. So stationary storage gives us more freedom in choice of chemistry. But, excuse me, the problem is the very low price point needed to penetrate this market. And even though I'm a professor, I understand price. If price is the problem, price must be the basis for the solution. Everybody else in academia says, let's invent a really cool chemistry and let's get published. But this doesn't solve social problems. If price is the problem, you have to invent to the price point. That means right at the beginning. And price is everything. You can see from this graph the various storage technologies as a function of price and the installed capacity. This is logarithmic scale. So this means below this line is essentially zero. These are differences without distinction. The only technology that works is pumped hydro. But pumped hydro is geographically limited. All of these other technologies aren't going to make it, including lithium-ion. Just far too expensive. So I want to show you that if we had storage today, you know, my talk is entitled Storage is the Key to Renewable Energies. Storage has enormous benefits even to today's grid. It would reduce price volatility. I'm going to show you an example. This is from the Midwest ISO in the United States, one day in the life. And it's color-coded. Red is the most expensive at $200 per megawatt hour, and blue is free. There's actually purple where they will pay you to consume the energy. All right? And this is what happens. This is about 4 p.m., and you can see things get more expensive through the day. But the most important thing to notice is here it's $200 per megawatt hour, and 30 kilometers away it's zero because of congestion. So with storage, you could eliminate these huge price fluctuations. Demand charges. You know, when you buy goods in the store, the more you buy, the lower the price. But with electricity, if you exceed a certain value, the price goes up because now you're straining the system. So with good storage, you could shave the peak. Reliability. We want to separate the feeder and the circuits. Whoops. I lost. This is an energy problem. That's better. You see, you just have to go with the flow, and it's all good. So if we could have every feeder and circuit operate autonomously from the generation and transmission assets, we have more stability in the grid. 10 years ago, in the United States, one tree fell on a transmission line in Ohio, and moments later, 55 million people were without electricity because the grid goes into all this saving mode. And congestion. It's huge now. Manhattan, for example, with all of the servers, the electricity demand goes up, 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 up. There's plenty of electricity in the New York area, but on the island of Manhattan, the transmission lines are near capacity. And you can't just keep sending more electricity because the lines get hotter and hotter until you will either melt the insulation or melt the lines. If you had energy storage in the basement of the skyscrapers at 2 a.m., you bring the electricity in, and at 2 p.m., you bring it out of the basement. And if you store enough electricity, you can sell to your neighbors. So the basement becomes a profit center. That's today. Now, tomorrow, right now the grid is designed for peak load plus reserve. If we have storage, we would design for average load plus reserve. And in most developed nations, peak is 40% higher than average. Imagine if we started an airline, you and I, and for 360 days per year, 40% of our airplanes are on the ground. And then for the other 5 days a year, all the airplanes are flying. You'd say that's a crazy model. But that's what we call the grid. And we figure about $17 trillion is going to be invested over the next 20 years. This is a huge saving. Microgrids. Microgrids without storage, not hitting their full potential. And lastly, renewables, wind and photovoltaic. When they're down around less than 5%, it doesn't matter. When they come in, we use them. When they go out, we compensate. But when wind and solar become major contributors, we have to mitigate the intermittency. Otherwise, they won't be contributing to base load. And that's the goal. We want wind and solar to be in base load. And storage is the key enabler. And you might ask me, well, how does a liquid metal battery compare with other batteries? It's no other batteries. It's battery versus combustion. It's diesel and natural gas. And diesel and natural gas are abundant and cheap. And there's no cost for venting CO2. So we have to think differently. We don't invent batteries like this and imagine how to make big arrays. That doesn't work. And I just want to make sure no one leaves the room thinking lithium ion. This is 20-year-old technology. It doesn't work. So we have to confine our chemistry to earth-abundant elements. That's how to make it cheap. Earth-abundant elements and simple manufacturing processes. So to make it dirt cheap, you make it out of dirt, and preferably out of local dirt. So you don't trade your dependence on imported petroleum for dependence on imported neodymium. If I gave you a battery that had 12,000 watt-hours per kilogram, but it comes from a remote, unstable part of the world, what good is that? And this is a graph. I apologize for this. This I took from the Wikipedia. Wikipedia is unreliable, but this one is somewhat reliable. This is a logarithmic scale, and it shows the concentration of elements in the Earth's crust. And these are the elements that are abundant. You know, if you're building photovoltaics out of cadmium telluride, and you notice that tellurium is about as abundant as gold, you've got a scalability problem. If you're going to build solar cells, you better be building them out of silicon, because silicon is the second most abundant element in the Earth's crust. These are the elements that I want to use. I forbid my students to go to this part of the periodic table. It's pointless. It won't scale. So why are you spending time? Why is there any research down here? It's nice for science, but it will not solve the problems because it doesn't exist. The material doesn't exist. Do you think that if we made something out of platinum, it's okay for jewelry, but it's not okay for industrial uses? Because do you think if the demand for platinum goes up by 100 times, the price of platinum is going to fall? No, it's going to go up because it's a constrained resource. Right here, all you need is this in the periodic table. I can tell you the future. It's right here. So now I want to talk about inventing the liquid metal battery. So pose the right question. I looked at the scale of modern electrometallurgy. As we heard earlier, aluminum is a huge producer of CO2. It's a huge consumer of electricity. This is a modern aluminum smelter. Row after row of cells, 960 Celsius, 500,000 amperes at 4 volts. Was invented simultaneously in the United States by Hall and in France by Héroult in 1886. They were both born in the same year and they both died in the same year, which means they were both same age in 1886, 22. They were both 22 years of age, and they took the third most abundant element in the Earth's crust and changed it from a precious metal into a common structural material. And how do we make aluminum? Bauxite imported, petroleum coke, 13 kilowatt hours per kilogram, $5,000 a ton capital cost, and we make virgin metal for less than $1 per kilo. That's an economic miracle. And I looked at that and said, what is the lesson for stationary storage? I said, how do I convert this into this? This consumes electricity. I said, can I teach this to store electricity and give it back? And the answer is yes. With internal funds at MIT, I invented this liquid metal battery. 3 liquid layers, light metal on top, molten salt, heavy metal on bottom. Electrolyte and molten metal looks a little bit like an aluminum cell, but I replaced the gas electrode on top with another metal. And what happens is magnesium wants to alloy with antimony. It comes down here, alloys, and produces current. And then to charge the battery, we electro-refine the magnesium back. We regenerate the battery every time. The battery actually gets better with use because it purifies. This was my team, one man. He looks worried. But then I was in Paris in fall of 2008 and raised some money from Total and then from the Department of Energy. So with $13 million, this was my team. Now he's smiling, you see? And this is multinational, everybody. All right, so this is a shot of the cutaway. This is about 2 centimeters here. This is antimony molten salt. This is one of my students, and this is former Secretary of Energy Stephen Chu, who'd come last June. But we had very severe restrictions on our research. We had to hit these goals, including price point goals. If we didn't hit these price point goals, they would terminate our grant. So this wasn't the normal academic offering. So these are the cells that we've built over time. This is about 1 centimeter. This is about, you can do the math. All right. Now, this is an example. This isn't magnesium antimony. We've gone to many different technologies. This is discharging in 2 hours. This is charge, discharge, 1 hour. 1 hour charge, 1 hour discharge. Fade rate, 0.005% per cycle, which is less than what we were supposed to achieve. Let's just achieve the goal. This means if you cycle it once a day, for 15 years, you'll still have 72% capacity. This is not like your cell phone battery. This has long lifetime. This is an interesting one, 1,000 cycles, cycle number and efficiency. For 200 cycles, we go 1,000 milliamps per square centimeter. This is 100 times the current density in a lithium-ion battery. It is 30% higher than the current density in an aluminum smelter. So you can use this as an instant load to balance frequency on the grid. Sometimes you need a load, not a source. This can be an instant load. You can shock it like this. This is the initial at 275. This is after. It seems to me it performs better after shock treatment than before. It loves abuse. So we've tested over 1,000 cells, many chemistries, new alloys, new salts, and many of them with less than $100 per kilowatt hour for the cost of electrodes and electrolyte. Capacity fade, very good. And then we wanted to accelerate the scale up to industrial. So I started a company, Liquid Metal Battery Corporation, and last year we changed it to Ambri. I know there's a village in Switzerland called Ambri. We didn't name it after Ambri, we named it after Cambridge. Right? So it was established to bring the technology to market, to build things faster, bigger, in ways that you can't do on campus. And my funding came unconventionally. First funding came from Bill Gates, who was watching my lectures on the internet and came to see me to talk about education. And at one point we talked about batteries. And he said, you know, this liquid metal battery, if you ever decide to spin out a company, let me know. Maybe I'll put some money in it. And he did. And then Total put money. So that was our start. And there we are, about 2 kilometers from MIT. And then this past year, we raised $15 million, again from Bill, Total, and from Vinod Khosla on the West Coast. So we have 35 people working at a facility about 900 square meters. And right now, we're establishing a manufacturing facility in Marlborough, Massachusetts. So this is the path forward. This is the cell. This is about 10 centimeters on edge. And then this is 25 kilowatt hours, 100 kilowatt hours. And this is about 20 meters long and has 2 megawatt hours. And we're developing all of the manufacturing capability, the power electronics, and so on. And nothing we can borrow, because lithium-ion batteries are so tiny that none of those power electronics are of any use to us. And the aluminum industry knows how to turn AC into DC. They have the rectifiers, but they don't have the inverters to go from DC back to AC. So we have to invent all of this. There's actually this is a little animation, a little entertainment for you to see how, this is why we have a startup company, to do this. You don't do this on campus. So this is 12 cells, we make the packs, and then the packs. This is all happening now. We just had this last week, the robots putting the caps on the cells, robotic welder. Okay, so this is now 25 kilowatt hours. This would be enough for one home. Solar panel on the top, and this is in the basement. And then you put these together, and eventually you'll have the whole thing. Oh, we'll give it about 30 seconds more. Okay, so this is now 100 kilowatt hours, and now you put this together with this wind or solar, and the footprint is small. You don't want to have a situation where the size of the solar field is X and the size of the storage is 10X. That's no good. The storage has to be compact. So this is 2 megawatt hours. And this is about the size of a 10-meter shipping container. Okay, so I think I've shown you the path to grid-level storage. It's silent. The gas-fired turbine is very noisy. No emissions, zero. There's no CO2 from diesel. No moving parts, which means you have a long service lifetime. All the flow batteries, they have pumps and so on. Pumped hydro has pumps. The pumps have to be replaced. It's remotely controlled. You don't have to have a human being go in. It can be giving current out, and then all of a sudden gets a signal from the grid to develop a load. You can have superposition of 2 electrical signals. So this can be playing in more than one market at once. And this is designed to the price point of today's electricity market. No subsidies. Now, I'm not waiting for oil to be $250 a barrel, and I'm not waiting for $200 a ton CO2 tax. I can't. This has to be designed to today's price point, otherwise it will not be accepted. So obviously we have to be somewhere below $500 or it's not going, and then it's a question of how far to the left we go. The farther left we go, the higher up we go. Everything is on this line. This is another scale. This is good. Good is down here, not up here. We want to be down here. This is pumped hydro. This is compressed air. Lithium ions way up here. We think we're in here. I haven't proved it yet, but so what's the next steps? We finished our work with MIT. From the ARPA-E, we're seeking new funding. And then I just show you a few things of what's going on. This is some new technology, 280, not only all liquid, not just liquid, liquid plus solid, all solid. This is 1,000 cycles flat, no loss of capacity. New technologies. This one here, 260, this is a polymer container. And then finally, at Ambri, commercial prototype by this time next year. And we are not going to have an Apple model where all of the product is made in one company in China. Batteries in the United States will be made in the United States. Batteries in Switzerland will be made in Switzerland using Swiss resources and Swiss labor. That's the model. So there it is. Electricity is modernity, and the missing piece is storage. Thank you.